Recording. Okay, welcome to our weekend Bucky call. And we're going to be doing spheres one more time today and seeing if we can understand the nature of the universe. Great. John Butler, how are you feeling today and what do you expect out of the call?
I'm feeling great. I've been out. I've had a lovely walk in Hyde Park and it's cooler, muggy, but cooler. We've had some very hot weather, 37s, 39s. We're now down to about 29, but a bit muggy. It may even get some rain today. Unlike the other side of Australia, we've been very dry. And I'm just interested. I'm enjoying exploring geometry. I still am not confident I understand the sphere completely, but hopefully by the time we finish today, my spheres and my tetrahedra will be all in order. So that's what I feel like. And Susan, so how are you feeling and what do you hope to take out of today?
I'm feeling great to be with you guys. After Wednesday's talk, I started listening to Euclid's Window again, so I could get deeper into geometry. Really appreciating that. I would like to take away how this is going to improve my worldview and my perspective on nature. Manu, how are you feeling and what would you like to get out of today?
Present this morning. Welcome, Kelly. I feel good. It is also very warm here in Cape Town. I'm on my boat here, and then with long views, trying to scrutinize the stars and see the structure. But to be more serious, really happy to learn more about geometry and especially geometry that appeals to my senses and to my applicability to the local in designing artifacts that improve the environment. So that's what I expect. Kelly, how do you feel? What do you expect?
I'm feeling like I can be here today. And I don't know, crisp for a while. As to what I want to get out of the meeting, I just want to hear what people have to say. So thank you. Joe, how do you feel? And what do you want to get out of it?
I'm feeling okay. It's a little bit cold here, but I'm overall I'm feeling okay. I'm excited. I want to learn more about spheres to keep building the momentum that we've been working off of, from triangles to spheres, and starting to have a better understanding of geometry of thought, and seeing how this relates to the way we think in everyday life. So Steve, how do you feel? What do you want to take away from today?
Well, I'm feeling really blessed. I'm not quite as hopeful. I don't know that I'll get to tetrahedrons today, or that I'll fully understand spheres, but I think I'm going to have a better understanding of spheres. And I'm really grateful for Susan, your insights, Joe, your insight, Manu, that your continued tutelage, Kelly, for your vision in this thing. And the reason why I'm going to pursue these spheres with complete all-out dedication is that somehow I'm going to be able to, and what my sense of it is I'm actually understanding life better. I'm understanding systems better. I'm understanding energy and how important it is.
Yeah.
And to building a business, to understanding thought. In fact, when do I know that my thought is well-grounded? Is this a real thought or is this just a fragment of something? And so this concept of geometry, I feel like I just don't want to let it slide. Many times in the past, I've taken synergetics and just kind of let it slide, saying, well, I'll understand that one day. And I'm really grateful for us core on the call who have said, okay, we're going to go for this. And I'm really grateful. So let's go for it today. And see who else joins us as we roll. We'll go back to spheres. I'm going to pull up the synergetics. Whoa, there we go. I'm having a little trouble with my keyboard and I went in to have it fixed this week. And so here's our topic of discussion. Synergetics 22407 sphere. Now we've gone through this, I think, twice already, but this time what I did was I read through it very carefully and I kind of color coded it. I color coded it because when Bucky talks, I think that sometimes he's passing a reference to something. And what I've tried to do here is color code this to say, okay, we've got a sequence of thoughts or ideas here, and some of these belong to each other more than the others do. I'm going to propose to you that the green ideas are kind of more contiguous, and that the gray ideas are kind of contiguous, and this green thing he kind of throws in and then goes back. And then he talks green stuff here, then he talks this, and then he goes here, and then there's some more green stuff at the end. So, you know, as John, I'm going to invite you to go ahead and read tonight. Let's read this one more time, pause at each sentence and see if you guys agree with me. Maybe let's stop here at sphere and just read everything above the blue stuff and make sure that you agree with me that Bucky is changing horses in the middle of the stream for a moment. He starts out with the Greeks, talks about his own ideas, and then goes back to the Greeks. See if you guys agree with me that he's inserting something here. And then as we go, we'll see if the colors match up, and let's talk about where these concepts, what he's trying to say. How does that sound, everybody? I sure hope so. Okay, John, do you want to start there with 224?
Yes, I'm right. Okay. The Greeks defined the sphere as a surface outwardly equidistant in all directions from a point. As defined, the Greeks' sphere's surface was an absolute continuum, subdividing all the universe outside it from all the universe inside it, wherefore the universe outside could be dispensed with and the interior eternally conserved. We find local spherical systems of universe are definite rather than infinite, as presupposed by the calculus's erroneous assumption of 360 degrees of surface plane azimuth around every point on a sphere.
So let's pause right there and make sure that we're all in agreement. I'm not sure what an absolute continuum is yet, so I'm open for feedback there. But
well, if you're traveling around the outside, it's never going to end. You can keep traveling around the outside of the sphere in any direction. It's a continuous and unending surface.
An absolute continuum. Does that mean I can walk around the sphere and come back to my beginning point again?
And head in any direction. It's not just around the center. You can wander around any point of it. You're still going to be, it's an unlimited surface. You could keep walking forever.
Okay, is everybody happy with that? Absolute continuum?
It means absolute continuum means there is no change of angle.
Okay.
Whereas we know that it is breaking. You know, if you have a line, the line is breaking in reality. So absolute continuum of 360 degrees means that it is smoothly, completely smooth at that surface.
Okay.
So, yeah.
Good. Any other comments or questions on that? Okay. Does anybody else see anything in this upper part here that you'd like to? I think it's harder to read with the blue stuff on it. Anybody see anything else up here that you want to talk about or just comment on that means something to you?
Well, on that, okay.
On this up here. Do you have a comment? Go ahead.
The other comment is that, you know, you have that division between the outer that is completely ignored and that actual fact never interact with the inner. The inner is eternally conserved.
Okay, really good. I think that's a really important concept. The interior is eternally conserved. It's separate from the outside. The outside can be dispensed with. There's no significance once we've defined our sphere. And of course, this goes along with the idea that the Greeks saw the stars as a giant dome. They saw it as a sphere. I did a little research and I to share some of this stuff, but the Greeks from in the 8th and 9th century, the two earliest Greek poets, Hesiod and Homer, both were flat earth believers. And so they believed in a flat earth. It wasn't until the 6th century when Pythagoras idea that there was a spherical earth, except that Pythagoras also believed that fava beans, because they gave gas and expelling gas took away the breath of life, that it was against his religion to eat fava beans. And at the time he claimed that fava beans contained the souls of dead people. So I don't think I want to consider too much about Pythagoras. That blew my mind when I read through that as I was doing some study. By the 5th and 6th century, most Socratic thinkers retained the flat earth model until the 4th century when Plato and Aristotle had developed some empirical evidence that that everything was round and in a dome, including based on his observations of ships as the masts would move below the horizon. In the 3rd century BC, Eratosthenes, 200 BC, calculated the circumference of the earth within 1 degree of accuracy by putting a stake in the ground, because he knew how big of a shadow was being cast at Alexandria. And then he goes back up to Athens or someplace and said, well, these are different size shadows. And using that stick in the ground shadow, predicted the spherical nature of the earth within 1%. I thought that was kind of interesting. Hope that was valuable to you.
I
So,
think
what's that?
yeah, I think what you're saying there is the expanding experience from the local.
Yes.
More and more kind of pushing away what I call the horizons of knowledge.
Yeah.
And in the process, actually changing completely the paradigm.
Right on.
Yeah.
Now, do you guys agree with me that this green sentence right here, this part of the sentence, he's now talking about his system and Bucky, and that really we could put this gray stuff together, because this beginning paragraph of this absolute continuum subdividing the universe outside from the inside, dispensing with the outside, is this calculus. These erroneous assumptions of 360 degrees of surface plane azimuth around every point on the sphere. So this gray goes with that gray, and that green goes with this green. Everybody good with that? For me, that was quite significant when I discovered that.
But when you speak like that, you forget the tango.
I forget the what?
The tango dance.
I still didn't get you, Bono.
Okay, the tango dance is this one. With the erroneous assumption, you nonetheless discover,
Yeah.
Truth, basically.
Yeah.
We find local spherical systems of universe are definite rather than infinite, are presupposed by the calculus erroneous assumption.
Yeah.
We had an erroneous assumption. We had it.
Right.
But we find that those two go together.
Yeah.
Right? So we marry the two in order to come to what it is.
Yeah.
In other words, we revise our assumptions based on our experience and our observation or whatever that comes to us. Look.
Yeah. It's not that the calculus was erroneous. It was that there were assumptions made about the nature of the universe when looking at that calculus, and it seemed to be applied to the nature of spheres and energy. And so the calculus wasn't bad, but the assumptions relating to it were bad.
No, what I'm driving to, Steve, is that if you didn't do those assumptions, probably you will never have discovered that it is that the local spherical system of universe are definite. If you didn't make the assumption.
Yeah, agreed. And it blows my mind that a wine dance that I can actually simulate a 720-degree-ness with my arm, with a cup with my arm. It boggles my mind, the serendipity of that. Anyway, it blows my mind. And here we have a Philippine local folk dance where they actually simplify that. They actually act out that 720-degree-ness, which is really quite profound. Okay, good. Any other comments or questions about the upper part of this sentence? All right, let's continue then from, let's continue then and eliminate the top. Let's just read the bottom part. And John, stop anytime you're inspired.
Sure, okay. So I'm starting from all spheres consist of a high frequency constellation of event points, all of which are approximately equidistant from one central event point. All the points in the surface of a sphere may be interconnected. Most economically interconnected, they will subdivide the surface of the sphere into an omni-triangulated spherical web matrix.
Right on.
Want to stop there or keep going?
I think we could stop there because I think we can look at some graphics about this, if you guys are okay with that. So down below here, I've talked a little bit about the Greekness of things. The Greeks defined a sphere as a surface outwardly equidistant in all directions from a point. And this was the idea of a dome. You know, all the stars on the dome are equidistant from the center. The Greeks actually thought that the stars were on a sphere, on a dome, actually a dome at first, but a sphere that went around the planet. And from a particular, and could be observed from a point from the position of the observer. I've got a really cool video, about 3 minutes, that I think are worthwhile, and it resolves the azimuth question as well. This was an absolute continuum. There are stars on both sides of the dome, both hemisphere. All the stars in the dome are equidistant from the center. I kind of put that all together, subdividing all the universe outside it from the universe inside it. Wherefore the universe outside could be dispensed with and the interior eternally conserved. In other words, there are stars on both sides of the dome in both hemispheres. All the stars in the dome are equidistant. An observer can see only one half of the dome, but wait, to the Greeks, there is no outside. It can be dispensed with. I have a video where we talk about this azimuth issue and resolve that, because we had some question on it last time. When I checked some definitions, when it comes to bearing can go either to the left or to the right. It can either go counterclockwise or clockwise. But when one uses the altitude azimuth system, one usually starts at the north and then goes around clockwise from 0 degrees to 90 degrees to 180 degrees to 270 degrees back to 360 or 0. And this little graphic here, this little thing will kind of demonstrate that. And that's not the one I want to show you. And of course, my thing is in the way. This is the one I want to, no, this is the one I want to show you. Okay, here we go.
Let's begin by defining the sky and kind of breaking it down so that we can get used to some terminology and directions. So here we are standing in an open field. We have north more or less behind us and south in front of us. I guess you could say we're facing toward the southwest, if you like. The horizon is just a perfect 360-degree circle, and the sky is suspended both above and below us. And the reason why I've drawn it below as well is because we know from our experience that there are stars and planets that have yet to rise. They'll rise later this afternoon and this evening. So we're going to go ahead and just represent the entire sky, even though we can't see it all. Now, the position that's directly above our heads is called the zenith, and the point directly beneath our feet, we call that the nadir. And if we take a circle and draw it from due north through the zenith to due south and back around again, then we can define a circle that will divide the sky into eastern and western halves. This is called the meridian. And this is going to be a useful reference point going forward. Now, while we're here, I'd like to just describe for you briefly how we can identify the position of any point in the sky from our perspective. So let's just say we have a star, and we can describe its position above the horizon. We do that by tracing a line directly to the horizon that's directly underneath our star and drawing an angle up to the star. So this angle is the star's altitude. And we define altitude as 0 degrees at the horizon and plus 90 degrees at the zenith. So the zenith is directly overhead. You could just draw a 90-degree angle from the horizon to the zenith. By the way, we can also describe the altitudes of objects below the horizon by using negative values. So it's 0 degrees at the horizon and minus 90 degrees at the zenith. Now we can also work out where along the horizon we need to look. And to do that, we start at due north and we just trace a clockwise angle until we arrive directly underneath our star on the horizon. And this angle is called the star's azimuth. So azimuth begins at 0 degrees due north, followed by 90 degrees due east, 180 due south, and 270 due west. And for this reason, since it's aligned to the horizon, it's sometimes referred to as the horizon coordinate system, or sometimes alt-azimuth, or alt-az, just for short. Anyway, if you could lie down, it would look like you're looking up into a giant dome. And that dome would look a little bit like this. This is what we would see if we had fisheye vision, or Stills and Ash were living in the northern.
I'm sorry for that. So I thought that was kind of helpful to share resolving the azimuth issues, which we talked about last time. Any comments or questions on that? Okay. From this point forward, as we start moving into Bucky, I'm overwhelmed with the old adage, as above, so below, that the very nature of the universe is represented in the sphericalness of in the sphere. And it really, it's bringing a reverence to my mind. So in the handout, I've got all this stuff here with links to those videos and stuff like that. So they'll be for the artifact. Now we're going to go for the Bucky explanation. And I think that this is the part you already read, John, right? Go ahead and read it again, if you don't mind. Let's go for it.
1 sec. Okay. This is 224.07 sphere. We find local spherical systems of universe are definite rather than infinite, as presupposed by the calculus's erroneous assumption of 360 degrees of surface plane azimuth around every point on a sphere. All spheres consist of a high frequency constellation of event points, all of which are approximately equidistant from one central event point. All the points in the surface of a sphere may be interconnected. Most economically interconnected, they will subdivide the surface of the sphere into omnitriangulated spherical web matrix. So the vector equilibrium is the zero starting point for happenings. It is the empty theatre and the empty circus and empty universe read to it. That should be accommodate, I think,
Yes.
any act and any audience. Okay.
All right. So now we're into Bucky. And this conversation, we can get into equilibrium discussions and a whole bunch of stuff, but basically these are graphics which kind of represent this thing. And if somebody wants to talk about this guy right here, Susan, Manu, you guys had a lot to say about this when we talked about this.
Is that the Genesia crystal?
Do I see a crystal?
I think that's the Genesia. Oh, yeah, I think the Genesia crystal, where you have the pentagons, the 4 pentagons.
This has squares on the outside here. And I don't know about 4 pentagons. This is kind of the figure right here. This figure and this figure are the same. It's called a Hube octahedron. It's free vector graphic, a free vector graphic. And this is a graphic that shows this collapse of the jitterbug in I don't know what this was exciting, but this is like the jitterbug conversation here. Now we had some good conversation about this Wednesday. This when we talk about vector equilibrium and all these points are equidistant from a central point.
I want to share something, Steve.
Yeah,
Can I show my screen now? I'll get
Please.
back to some stuff that I have here.
yeah, I'm going to do what I can to pin you on the screen so that we
Yes.
can see it.
Do you see this?
Yes.
Do you see it? This is a geodesic dome, a model of it.
Right.
Now you have on top on it colors, white and I'll call it yellow, white and something else. You
Yeah.
see that?
These are
Right?
the pentagrams. These are the pentagrams that Susan was talking about.
Okay. Now, you see the white triangles are equilateral.
Okay.
You see that they are interconnected at one vertex, each to the other. If I turn it the same, it's same here. And it will go down. This is half of it, right? So that's the array. If you just take the omni-triangulated, that is the maximum expansion. And then in between, you have pentagons. You see this pentagon?
Yes. Everybody see those?
Yes.
But in the most expanded state, these pentagons do not in reality exist. They are voids because they are in there because this thing can fold in back into something else. And this was Bucky's innovation to fill that void with pentagonal structures. You see me?
Yeah.
Therefore, when you do this, it becomes very resilient. I'm pushing here, really strong. You get it? And this is paper. This is nothing but paper. Individually, any of these things, any of these triangles will kind of be folded easily. So this is the association glue of equilateral and isosceles in a certain proportion. That's how Bucky built the geodesic dome. This is a model, and you can build it yourself if you want.
Right.
So in the omni-triangulated, what you say, the empty theater, Steve, your comment, in the empty theater, we can conceptualize it in that these pentagons don't exist. So you just have the expansion in a way that it is most economic and that no, not most economic, is expanded, and this triangular interconnect, they are all connected. They interconnect in a way that is stable, that is in equilibrium, but unstable. Do you understand what I'm trying to say? If I remove this pentagon here, all of them, I will still have my equilateral triangles that are interconnected, but it will be very unstable. That is a vector equilibrium. And I have stabilized it by adding these pentagons, this pentagonal, filling the pentagonal space to make it a dome, the geodesic dome.
Right.
Right.
When I build my pentagon with magnets, it's not flat, right? There's a it makes it a little bit concave. Is that correct?
Yes.
Yeah.
But you cannot build a pentagon with equilaterals.
Yeah.
So-
Now let's make it clear.
You have to build it with isosceles.
An isosceles triangle has two equal sides and two equal angles, but the third side is not the same as the other
Exactly.
two.
Yes. So when you glue the edges, it will give it the curvature.
Joe, did you start to say something?
No, I was just thinking about how if you were to separate a part from the whole, how it actually, the whole itself actually gets weaker. And that's kind of holds true in systems analysis as well. If you look at one particular area as opposed to looking at the whole, then you can, when you're analyzing it, if you only focus on one part, that the whole may actually get may suffer as a result. So if you're not looking at things as far as how they're connected, then so I'm thinking in terms of like just an organizational dynamics. If you were to only look at one aspect of it as opposed to how all the parts are related to one another, then you're essentially saying that you're not necessarily going to answer the problem that you're trying to solve, if that makes sense. It's a little abstract, but I could give a more concrete example.
No, I
Like,
think so.
yeah, so anyway.
If you have more to say, go ahead and say.
I'm just thinking about it in terms, if you were to look at something in terms of you have a problem with, I don't know, something in production and not necessarily understand your supply chain or something along those lines. You
Yeah.
only look at one area, then something else could go wrong possibly. This is just the idea of pulling the parts, pulling the whole, looking at the whole with, and then when you're pulling parts out of the whole, the whole system could actually get weaker, if that makes sense.
Yeah. Cool.
Joe, it makes sense in this, like when Bucky decided to fill that void in the model with the pentagonal structure, it was like it was adding to it the synergistic part of energy that wasn't there with just the part joined in single bonding at top of each other.
Yes.
At the vertices of each other. You get what I'm trying to say?
Yes. Yes.
That is adding back now to make a synergistic structure.
Right.
So do you want to hold up your dome again, Manu? Because I'm a little bit confused. I just built a pentagon out of these magnets, and I'm using equilateral triangles. They're all the same. And so I have a dome here, quite a bit of a dome made, because if I'm making a pentagon, these base laterals need to be a little bit longer in order for this thing to be flattened out. What's the non-equilateralness of the isosceles? How much bigger or smaller are they from the equilateral triangles in between those pentagons?
There is a ratio of this base to the side of the axis of the equilateral or the isosceles. I can't remember. There is a ratio.
There's a ratio.
Yes.
Okay, cool. So there's a mathematical formula that says how long.
The two sides of the isosceles, the two equal sides of isosceles are the same as that of the equilateral, as you can see here.
Yeah, and so the
base is different.
Well, I don't know, because the base is the same size as the equilateral triangles. Obviously, I can see that. So therefore, the things that are branching off, those must be a little bit different in size, because the base of the pentagon is equal to the equilateral triangle.
Yes.
So that's the reason why this one sticks up way high. And these guys up here on the top need to be shorter in order to get this thing to go down to match your dome. And there's a mathematical ratio for that, you're saying?
Yes.
Okay. That's okay. I don't
Wait.
think I need to know it. If you told me, I wouldn't remember it. What, Susan?
Why would you want that to be flat? I mean, the whole idea of the structure is that it pops up out of a plane and it has structure in 3D.
I don't want it to be flat. I'm just noticing like this guy right here is flat. When I build a hexagon out of this, that's an equilateral hexagon, everything's flat. But when I make it into a pentagon, I have to take out one of these guys and connect it. And as soon as I do that, then it gets to be,
Like
Curve. It's curved,
Just-
yes.
yeah, it
just
starts
like
to
it is
curve.
at the top of Manu's dome.
Say again?
And that's what's going on at the top of Manu's dome.
That's
Is-
right. It is
The
fine.
only difference is that in the model here, there's a ratio that gives, I mean, that top not exactly the same as Steve's, but that's the principle.
Yeah. Well, I learned something about magnets and pentagons and hexagons tonight. It seems to me I built another structure where I tried to get it to come together and it won't. Kelly built one of those a while ago. Do you know what structure I'm talking about that doesn't quite come together? Okay.
But I think that what is the most important there is that in order in Steve model to have a curvature, you need to knock out one of the segment.
Right. I got you.
Otherwise, it was flat. In order for you to have a curvature, you physically remove one of the sticks.
Which I did do. As
Yes.
soon as I remove when I have 6 in here, it's flat. If I put one up here and another one over there, I can make this into a hexagon really cool. But if I take out that extra triangle right there and I connect these, I now have quite the little pointy thing. And what you're telling me is that these edges are not equidistant. They're not equilateral. They're a little smaller, and there is a mathematical ratio that would be.
And what I want us to grasp here
Yes.
is the link between finiteness and curvature.
Okay. Now you mean
When you put again your 6.
my 6th
Just-
one? All
yes.
right. Here it comes. Here's my 6.
Yes. If I'm an ant in the middle there, it's flat to me. It is
Yeah.
infinite.
It is flat.
All right.
Yeah.
Right.
As soon as I knock one out, if I knock one of things out,
Oh,
My universe just crashed. I just had a catastrophe. I'm using the thin magnets. I'm not using the thick magnets, so they're not quite as stable.
okay. But the concept is this one. As soon as I knock one out, all of a sudden is no more infinite. Because
There's no
I
more-
can see,
There's no more infinite. Is that what you said?
yes.
Yes.
All of a sudden, me and ant, I can see that there's one side and the other side. And that there is one.
That's a neat
I
insight.
can see the mountain. I don't see anymore just a flat.
I see.
So you
As
added,
an ant, as soon as you knock out the dimension, I can see the mountain.
Yeah. So what were you saying, Susan?
So if I see the mountain is a consequence of some angle or curvature, and the angle also tell me and that consequence will also tell me I infer that it's finite. It's not infinite.
Okay. Now I'm going to say what you just said another way, but I want Susan to go ahead and say what she was saying. Susan, you had a comment.
so it almost in Manu's example, the ant was a flatlander.
Yes.
So when you when you added in the curve, you gave it you gave it a relief, you gave it another dimension.
Yes.
You added a dimension with the curve.
Yeah, that was my epiphany as well. In other words, what I think, Manu, what you're saying, this is all equilateral and it's basically infinite. Another way to say it is it exists on a 2D plane. It is not 3D.
Yes.
In order to make it 3D, I've got to make it not uniform. I got to take out one of these puppies And as soon as I take out one of these puppies, I now create a hump that is no longer, it is no longer two-dimensional or infinite. It is now three-dimensional because it has a little pooch to it. I think
Yes.
Susan and I just said the same thing, and that was the epiphany that you shared.
Right.
Whoa, beautiful. Comments, questions? Is everybody getting this, or is it all just on my side of the Zoom?
Nelson,
Me and Susan, our time zones are different, but our pentagons are doing just great. Any comments or questions on this?
I think I'm back again in the Euclid's window book and kind of looking at the history of geometry.
Yeah.
What I think that I'm getting is that there was initially moving from Egyptian to Greek, there was very much this planar, and in fact, Euclidean geometry itself is defined as planar geometry. And so it really wasn't until people began to work with that for a number of centuries that they got to the level of sophistication that they could start grappling with curves, they could start taking things into other dimensions.
And I think it was actually with the invention of imaginary numbers, when they decided that, hey, we can put an imaginary number so we can get out of this 2D plane, we can go into a 3D thing by taking our real numbers on a 2D plane, and we can stick an imaginary number in out here in the universe someplace, and blammo, we have 3 dimensions now. I think imaginary numbers had something to do with it. I could be wrong.
but
very
it's
cool.
also important to notice that I see the hump
Yeah.
inside.
Yeah.
And I imagine the hump from outside.
Yeah.
My mind, this is a principle of induction here.
Okay.
I have my life local. Then I realized that there was a mountain. But for me to realize that it is a mountain, I needed to be out.
Yes.
I needed to imagine myself out of it and seeing it to realize that there is
Right.
a mountain. So the in-out simultaneous, working as a duality, is again in operation here for that discovery.
Right. And I had something come up from there. Comments, questions on what Manu just said? Oh, this brings us back to our very first discussion when we started this up with angular topology, the difference between topology and topography. Topography tells me where the mountain is, but it's topology that defines what a mountain is. Topology says, oh, this is different from that. Topography says, well, this different thing is here and not there, but topology describes that differentiation. I hope that made sense. That's what's come to me over the last couple of days, and I just thought of it again the other day. Comments, questions? Okay, the other thing I want to bring up is this concept of equilibrium. Because to me, equilibrium has always meant, I would say, okay, we've got a structure here, everything is balanced, it's permanent, therefore we have equilibrium. But I've been learning that this is not equilibrium. That equilibrium is something else. Is that true?
I think there is a distinction. You know, there's generalized equilibrium is more generalized than stable.
Say that again.
Equilibrium is more generalized than stable. In other words, you can have unstable equilibrium.
Okay.
Like the vector equilibrium is unstable.
I see.
So a stable structure is a special case of equilibrium.
Yes.
Ah. So this is a demonstration of equilibrium, and it's a special case.
Yes.
And in Bucky's universe, equilibrium is a place where anything can happen.
Equilibrium is the instantaneous switch.
Right.
You get what I'm trying to say? It cannot
Yeah.
stay there. You know, you have evolution, you have deformation, whatever,
Right.
and it is there. It arrived at, you know, like they just say minute
Yeah.
time where everything seems like to be, but it doesn't stay there. It's unstable, changes.
Yeah.
Like the point of change of phase. When you have the tetrahedron concave and the tetrahedron convex.
Yeah.
So the point of change when the two like this and is converted, the tetrahedron is converted from here to there, it is an equilibrium that is unstable. It's just in there, out, in, out.
And I think Manu's talking about vector equilibrium in particular.
Yes. Or when you switch your light on, you switch it on, it goes from one state to the other through some equilibrium that is unstable. Unstable also means biased.
Okay. So I want to come back before we proceed because I don't want to leave this point. I want to reaffirm this epiphany that when this object is a hexagon and exists only on two planes, Bucky would say that there's an invisible aspect to this and it's not definite. But when suddenly there's this hump in it and I have this third dimension, then it becomes definite. It becomes defined. It becomes finite.
Yeah.
So
is local.
And it's local. It
Yes.
because it's an event occurring right now in this place.
But
And it's,
in Becky's language, an event is always a constellation,
yeah.
many
And-
arrays
And so-
that intersect and
okay.
materialize locally. That is structure.
And so as soon as I disconnect this otherwise definite structure, I now create a state of equilibrium where anything can happen. Does that sound okay?
So tensegrity is an example of an equilibrium.
Okay.
It's just if it's in tensegrity, by definition, there's a balance between the compression and the tensile. And
Okay.
so those forces are balanced. So it's an example of an equilibrium.
Yeah.
The vector equilibrium is an example of an unstable equilibrium.
Right on. And
Balance for that second, but it's not equal. It's
And
kind of a balance point.
And tensegrity relates to tension
And compression,
and compression.
the balance of those two forces.
Yeah. Yeah. And I relate that somehow to the human aspect of intention. If I have tension, there's obviously some contradictory going on between what I see now and some potential. And as long as I have that inner tension, I'm going to be frustrated and upset. And as soon as I can take that inner tension and focus it to become an intention, that's when I begin my experiment. I have a thesis and I go out with my intention to resolve the inner tension and maybe come up with some tensegrity. Anyway, I'm just using the words kind of like in parallel. This is what I'm understanding. Go ahead.
We apply it very well. I mean, you take judo, for example, or wrestling.
Okay.
Right? You have unstable equilibrium all the time. When they are holding, you know, like you're trying to
Right.
ippon.
Right.
But when you ippon, the ippon is stable. That's why it's counted as a point.
Aha.
You see, in judo, the points are counted when you ippon, meaning that you immobilize
Right.
your adversary with a move on the floor.
And while I'm wrestling, I'm in a state of equilibrium. And then when
But it's unstable. Yes, it is doing this until one of the players, pam,
And
Tell the audience.
then I have equilibrium. My opponent's on the floor. I have a local event with a
Yes.
different kind of equilibrium going on.
Exactly. It's counted as something. It's counted as a point.
Yeah.
A point that is towards the result.
Comments, questions? And I want to come back to this. I hope I paused long enough. You guys got to jump in if you have a comment or a question. John, did you have a comment or question? You kind of smiled when I said that. Did you have it? What's coming up for you, John?
I'm just thinking of my spheres and of Bucky's triangles and of the parts of what you're saying that is or isn't part of a sphere, because you've gone out of spheres, back into spheres. I'm just contemplating the sphere.
Well, and John, you're going to be rewarded because there is only spheres. That's all there are. There's 720 degrees happening everywhere. And we're going to see something about that. And maybe now is a good time, but I want to show one more thing before I go. Okay. So we talk about finite and infinite. We talk about visible and invisible. And right now we have a bow tie here. And we have both sides of this are finite, visible, definite. But you know what? If I have just this guy, that's all I see. This guy is out here, convex. I just can't see him. But this guy wouldn't be here if this guy weren't here. I just thought I would say that. I'm not sure I understand what I just said. Comments, questions? Comments, questions? Okay, good. It's just, hey, if any of you guys get a brain fart, go ahead. Let's hear it, you know? So we go ahead. All right. I want to share something, reward John for his comment, bringing us back to spheres. I think what you're about to see blew my mind. What you're about to see blew my mind. And so let's see if we can go here.
Sit down.
All right, here we go. I got my thing going. Here we go.
You know, unlike a battery, the electricity in the grid comes in the form of alternating current, or AC, which means electrons in the power lines are just wiggling back and forth. They never actually go anywhere. So if the charges don't come from the power plant to your home, how does the electrical energy actually reach you? When I used to teach this subject, I would say that power lines are like this flexible plastic tubing, and the electrons inside are like this chain. So what a power station does is it pushes and pulls the electrons back and forth 60 times a second. Now at your house, you can plug in a device like a toaster, which essentially means allowing the electrons to run through it. So when the power station pushes and pulls the electrons, well, they encounter resistance in the toaster element and they dissipate their energy as heat. And so you can toast your bread. Now, this is a great story. I think it's easy to visualize, and I think my students understood it. The only problem is it's wrong. For one thing, there is no continuous conducting wire that runs all the way from a power station to your house. No, there are physical gaps. There are breaks in the line, like in transformers, where one coil of wire is wrapped on one side, a different coil of wire is wrapped on the other side. So electrons cannot possibly flow from one to the other. Plus, I mean, if it's the electrons that are carrying the energy from the power station to your device, then when those same electrons flow back to the power station, why are they not also carrying energy back from your house to the power station? I mean, if the flow of current is two ways, then why does energy only flow in one direction? These are the lies you were taught about electricity, that electrons themselves have potential energy, that they are pushed or pulled through a continuous conducting loop, and that they dissipate their energy in the device. My claim in this video is that all of that is false. So how does it actually work? In the 1860s and 70s, there was a huge breakthrough in our understanding of the universe when Scottish physicist James Clerk Maxwell realized that light is made up of oscillating electric and magnetic fields. The fields are oscillating perpendicular to each other, and they are in phase, meaning when one is at its maximum, so is the other wave. Now he works out the equations that govern the behavior of electric and magnetic fields, and hence these waves. Those are now called Maxwell's equations. But in 1883, one of Maxwell's former students, John Henry Poynting, is thinking about conservation of energy. Now, if energy is conserved locally in every tiny bit of space, well, then you should be able to trace the path that energy flows from one place to another. So think about the energy that comes to us from the sun. I mean, during those 8 minutes when the light is traveling, the energy is stored and being transmitted in the electric and magnetic fields of the light. Now, Poynting works out an equation to describe energy flux. That is, how much electromagnetic energy is passing through an area per second. This is known as the Poynting vector, and it's given the symbol S. And the formula is really pretty simple. It's just a constant, 1 over mu naught, which is the permeability of free space, times E cross B. Now, E cross B is the cross product of the electric and magnetic fields. Now, the cross product is just a particular way of multiplying two vectors together, where you multiply their perpendicular magnitudes, and to find the direction, you put your fingers in the direction of the first vector, which in this case is the electric field, and curl them in the direction of the second vector, the magnetic field. Then your thumb points in the direction of the resulting vector, the energy flux. So what this shows us about light is that the energy is flowing perpendicular to both the electric and the magnetic fields. And it's in the same direction as the light is traveling. So this makes a lot of sense. Light carries energy from its source out to its destination. But the kicker is this. Poynting's equation doesn't just work for light. It works anytime there are electric and magnetic fields coinciding. Anytime you have electric and magnetic fields together, there is a flow of energy, and you can calculate it using Poynting's vector. To illustrate this, let's consider a simple circuit with a battery and a light bulb. The battery by itself has an electric field, but since no charges are moving, there is no magnetic field. So
You see the spheres, John? Here we go. We're about to see spheres everywhere. Here we go.
the battery doesn't lose energy. When the battery is connected into the circuit, its electric field extends through the circuit at the speed of light. This electric field pushes electrons around, so they accumulate on some of the surfaces of the conductors, making them negatively charged, and are depleted elsewhere, leaving their surfaces positively charged. These surface charges create a small electric field inside the wires, causing electrons to drift preferentially in one direction. Note that this drift velocity is extremely slow, around 1/10 of a millimeter per second. But this is current. Well, conventional current is defined to flow opposite the motion of electrons, but this is what's making it happen. The charge on the surfaces of the conductors also creates an electric field outside the wires, and the current inside the wires creates a magnetic field outside the wires. So now there is a combination of electric and magnetic fields in the space around this circuit. So according to Poynting's theory, energy should be flowing. And we can work out the direction of this energy flow using the right-hand rule. Around the battery, for example, the electric field is down and the magnetic field is into the screen. So you find the energy flux is to the right, away from the battery. In fact, all around the battery, you'll find the energy is radially outwards. Energy is going out through the sides of the battery into the fields. Along the wires, again, you can use the right-hand rule to find the energy is flowing to the right. This is true for the fields along the top wire and the bottom wire. But at the filament, the Poynting vector is directed in toward the light bulb. So the light bulb is getting energy from the field. If you do the cross product, you find the energy is coming in from all around the bulb.
Tons of
It
spheres.
takes many paths from the battery to the bulb, but in all cases, the energy is transmitted by the electric and magnetic fields.
People seem to think that you're pumping electrons and that you're like buying electrons or something, which is just so wrong. for most people, and I think to this day, it's quite counterintuitive to think that the energy is flowing through the space around the conductor. But the energy which is traveling through the field, yeah, is going quite fast.
So there are a few things to notice here. Even though the electrons go two ways, away from the battery and towards it, by using the pointing vector, you find that the energy flux only goes one way, from the battery to the bulb. This also shows it's the fields and not the electrons that carry the energy.
I mean, how far do the electrons go in this little thing you're talking about? They barely move. They probably don't move at all.
Now, what happens if in place of a battery, we use an alternating current source? Well, then the direction of current reverses every half cycle. But this means that both the electric and magnetic fields flip at the same time. So at any instant, the pointing vector still points in the same direction, from the source to the bulb. So the exact same analysis we used for DC still works for AC. And this explains how energy is able to flow from power plants to homes in power lines. Inside the wires, electrons just oscillate back and forth. Their motion is greatly exaggerated here, but they do not carry the energy. Outside the wires, oscillating electric and magnetic fields travel from the power station to your home. You can use the pointing vector to check that the energy flux is going in one direction. You might think this is just an academic discussion, that you could see the energy as transmitted either by fields or by the current in the wire. But that is not the case. And people learned this the hard way when they started laying undersea telegraph cables. The first transatlantic cable was laid in 1858.
It only worked for about a month. It never worked properly.
There are all kinds of distortions when they tried to send.
Enormous amounts of distortion. I mean, they could work it at a few words per minute.
What they found was sending signals over such a long distance under the sea, the pulses became distorted and lengthened. It was hard to differentiate dots from dashes. To account for the failure, there was a debate among scientists. William Thomson, the future Lord Kelvin, thought electrical signals moved through submarine cables like water flowing through a rubber tube. But others, like Heaviside and Fitzgerald, argued it was the fields around the wires that carried the energy and information. And ultimately, this view proved correct. To insulate and protect the submarine cable, the central copper conductor had been coated in an insulator and then encased in an iron sheath. The iron was only meant to strengthen the cable, but as a good conductor, it interfered with the propagation of electromagnetic fields because it increased the capacitance of the line. This is why today most power lines are suspended high up. Even the damp earth acts as a conductor, so you want a large insulating gap of air to separate the wires from the ground. So what is the answer to our giant circuit light bulb question?
Okay, so it proposes an academic question at the beginning of this thing, and he'll take a while to resolve it here at the end. And I think that that's beyond the point.
After I close this,
did you guys, his point is that the power actually goes from here to here, and the length of the wires is irrelevant. He doesn't demonstrate that very well other than through all the circles and spheres that he drew in those cool drawings. Any comments or questions about this for you guys? This blew my mind.
I think his point is more than that, Steve.
Yeah.
He's talking about the arrays in the first place.
Okay.
It is fields, right?
It's what?
And then let me ask you a question. If the energy field flows into the lamp as you had there, then what is light?
Yeah, yeah, okay. The thing, okay, do you want to answer that question or is that rhetorical?
It's an equivalence.
Yeah.
It is an equivalence.
Yeah.
Light and energy are
Right.
equivalent in my opinion.
Yeah.
Or a what, Manu? I don't understand that last word.
Light and energy. You saw on the
Yeah.
diagram,
And equivalent.
R-A,
energy field was going
Equivalent.
from the battery to the light bulb.
It's the
Right?
same thing. He's saying it's the same thing.
equivalent.
Yeah,
The
equivalent.
word.
So what do we see? We see light.
Yeah.
So what is light?
Vibration.
is, yeah.
at a certain frequency.
But I think the most important point of this here is that you have an interaction of different fields.
Okay.
Different to result into something that is structured locally for us to see, for us to measure. You get what I'm trying to say?
Yeah, I
Because
think so.
then we are measuring, we measure electricity, right? But we measure electricity because the electric field and the magnetic field interacted together to produce the energy field, to result in the energy field that travel from one point to the other.
Right.
Locally, in a way that we can put a gauge and measure what is going in.
Right on.
Via Poynting flux equation, the
Right.
energy flux. Yes.
Right. And I thought it was cool. The guy's name was Pointing, and he's telling us what direction the energy is pointing. I thought that is, his mother should be just overwhelmed with that. Does anybody else get anything out of this conversation? What about the outside inside conversation that Bucky's having? What would the Greeks have done to everything outside the wire? What did Maxwell want to do? It was Maxwell, I think. No, Lord Kelvin. What did he want to do with what was going on outside the wire?
Not consider it.
He didn't want to consider it. Hey, no, the electricity, what we want, the electromagnetic signal is going through the pipe. He said, nothing's going on out here. And two other guys said, nope, it's all going on outside. So if we take the Greek posture and we forget about what's going on outside, we don't have electricity. We would
Local
have
boundaries.
go ahead.
Local boundaries.
Yes.
Which sphere are you willing to consider?
Yes.
I think that is more natural. Energy flows outside of a cable. Energy didn't flow in the cable, it's outside of a cable. Therefore, what is important? What is the impedance to energy? What do we feel? It is the change or the measure that what we're going to measure at the boundary.
Yeah.
Do you understand that, Susan?
So I think of impedance as resistance within the circuit.
Yes, I'm just saying, but we are going to measure. You know, finiteness also implies impedance, isn't it?
Yeah.
Because it implies, and boundary imply impedance, because boundary says this is the fence.
This is the inside. Everything outside is outside.
Yeah.
Yeah. And the beautiful thing about it is that what's going on outside is what's making that happen. I think that correlates with every aspect: business, thought, relationships, you know.
That's what I'm trying to relate it to, and I'm struggling. I'm struggling a little bit with that.
Well, let's talk about that.
I think what you just got was a prime example of how important perspective is.
Yeah.
You have to have a distracted perspective to be able to consider outside. And outside is all defined by where you put the boundary to begin with.
Exactly. And if I establish this is my reality, I have myself over here, and and now all of a sudden I have otherness. If I see otherness as just this connection here, I'm missing out, because the otherness is all outside here. I have a business. What's going on outside here is what's making that edge happen.
I think that's why Bucky had in, out, around, and between.
Exactly. Comments, questions?
Well, hold up again. What you had, Steve?
Yeah.
Hold on. You know, the stick is just the strut. Yes, the stick is just the strut of a structure.
Yeah.
Right? Right?
Yeah.
What is going on? Yes, and that's why we say Bucky is always interested in relationship and interrelationship.
Yes.
I made a comment there on the chat of a Greek watching the movie of life in an auditorium. Their perspective was that of a spectator. Bucky was a player in the soccer field of life. Do you see a difference? The Greek, when there's a football match in the US, you know, the final of whatever, college football or whatever, they were spectators. They sat in the auditorium and they were contemplating. Bucky is not that. Bucky is one of the players who is going to touchdown, who is going to tackle, who is going to run, who is going to do this and that. That's what it is. That wise, you are obliged to every time be alert on the move of other players and the energy distribution in a way that it is changing all the time. And that is the perspective of Bucky's geometry, is relationship and interrelationship, always changing, always flowing, always going from one actor to the other, and always considering the position of other actors in reaction to that. That is always at play. Action, reaction, resultant. Action, reaction, resultant, feedback. Always, always, always.
And it's a result of this call that I have basically made a major effort in my life not to use the word relationship, but to use the word interrelationship, because it really does indicate a more complex way. I can be very egotistical about my relationship with you, but suddenly I'm not so easy to be egotistical about my interrelationship with you, right? Otherness becomes critical to the conversation.
Yeah, I think that is really the link. You know, like before mathematics and geometry, they were like a world out there. But with Bucky, you have the interlink with the social. Really, I mean, you can't do Bucky geometry without feeling the social around you playing and without feeling being in the social field and being one of those things that have been moved. You can't.
And he spent the latter part of his life totally putting his energy into making everything work for everybody. I mean, that was his mission, is that nothing gets left out. And what we see as pollution is simply something we don't understand yet. Let's look at the system, figure out what that is, so that everyone benefits. Go ahead, Susan.
It's just what's left over.
Yeah. Yeah. Okay. Any further epiphanies, comments, questions? Nelson, I've seen your head bobbing a couple times. You got anything going on? I don't want to put you on the spot, my friend, but what's going on for you?
Yes, thank you. I don't have a question or comments. Okay. In my opinion, yes, in my opinion, the energy is flowing all time, all time. Is when have a resistance, see? Resistance. Okay, it's difficult because the energy not flow, not flow. It's very interesting for me about the equilibrium, convex and concave, concave and convex. It's the equilibrium. I don't know why. Okay. It's a question. Okay, why is an equilibrium in the tetrahedron, concave and convex? I don't know. I don't understand.
Yeah. Comments or questions?
Isn't this to do with insideness and outsideness? The sphere contains space inside, but one of the biggest differences for Bucky with me is he's constantly thinking of the other side. You're not just getting one triangle, you're getting the other side. You're not just getting the contents of the sphere, you're getting what's outside. It's nothing is one, nothing is alone. There's always at least the reverse or the other side of it.
Yeah. I just, go ahead.
Okay, in my opinion, the equivalent not exists, not exists. Exists some harmony. Yes,
Yeah.
I don't understand.
Harmony is a good word. Joe, did you, somebody else was saying something?
So I understand the perspective aspect and how the inside and outside, how to look at things. I'm trying to figure out how would Poynting's vector analysis work outside of what we've just witnessed. Like what other areas it could be applied to. Like that's what I'm trying to figure out. So how would Poynting's vector analysis, that it essentially is, talks about energy transfer. How could that be applied to another domain?
I have an idea on that, because that little signal that he used like this, where you take your hand and you put it in the direction and it goes like that, that same metaphor is used describing torque. If I take a wheel and I spin it around, it's established, becomes a gyroscope. And what direction does that go in? It goes in that direction. Exactly the same metaphor is being used. So think of torque.
So I think of Kelly's saying that energy always flows to the line of least resistance. Energy flows. And so I think that it probably is really a good part of evaluating your perspective to see if you can see which direction the where are the resistance points, how is the energy flowing? And I like to use that sort of an idea when I look at social situations, work situations.
But I think I also think this, if we reflect on the movie, that with the video that we just watched, and that we have some conceptions of things that are erroneous.
Right.
And then we act following those, and we're not able to grasp the real consequences of it. Like to think that energy is transported through the cable, right? Maybe if we knew that in actual fact energy is radiating outside of a cable, maybe our social construct would be different. For example, planning a city. For example, you've seen today in terms of town planning, from the experience of transporting the first transatlantic cable from New York to the US, to the UK. Right? It didn't work. Yeah. In consequence, you have cables that became aerial, and in cities you had corridors because they knew that there were effects of energy around that cable.
Yeah.
You had clearances and reserve areas and minimum defined to build it. So houses are a certain distance from lines. Even today, when you have high tension lines going across an area, you don't build just underneath it, unless you have squatters who come and build on it. Is unsafe. You understand what I'm saying? That is one. The other thing is that we design technologies now that allow you to bury cables on short distances
Yeah.
and lose the minimum energy. Most of electric cables in cities today are buried.
Yeah.
You get what I'm trying to say?
Yeah.
So, but was, in my opinion, as a consequence of that experiment, that it didn't work. There was something else.
Well, I
So
think
to
there's
me,
another
that is very important. Yeah.
I think there's another factor. As I listened to the end of that video, when he explains that the actual electromagnetic energy is transferred from the source to the appliance directly, and that the amount of wire doesn't matter, and he actually proves that with a formula about 1/c some stuff that I didn't get. But I came back to Nikola Tesla, who was offering free energy transfer, thought energy could be transferred without wires. And Edison and Westinghouse and all those dudes said, well, hell, if we don't need a wire, we can't charge. So they took Tesla's technology and buried it because they could sell wire. They could control wire. And that's a revelation that thing gave me, and that upset me. So I think we're going to see a time. They're now talking about getting electricity out of water. You know, they're talking about getting the fourth phase of water, where all the electrons build up and it just becomes a battery, right? There's energy everywhere around us. And right now, our corporations have created these monopolies and have restricted the development of science in directions that lead them away from their monopolistic control. Sorry to get so political.
No, it's that perspective thing. So one of the books I went through last week was called Confessions of an Economic Hitman. And he was talking to some native peoples who were initially, at one point, they were saying, but we'll never have telephones because nobody will ever bring telephone wires to the Amazon. And then what do you know? The technology leapfrogs. Now you just have the satellite bouncing it down. You don't need the wires.
Yeah. Beautiful. Maybe we could do the same thing with electricity.
You could.
Yeah, except for our utility companies. Is anybody interested in this torque thing? It's a 3-minute video, and it's all about spin and torque. It has to do with Bucky's 6 degrees of freedom, and it relates directly to this idea of this hand thing. And it's a 3-minute video, so I really feel to share it. Is everybody okay?
One more thing, Steve.
Okay.
Before you go, did you see the interrelation between the local and the generalized?
Yeah, maybe. Yeah.
In that the move of electron was very slow.
Yeah.
Local.
Yes.
Right?
Right.
But that created an electric field.
Yeah.
That
facilitates the electric field. Yeah.
Yes. And it created the electric and the local magnetic field.
Yeah.
That allow the energy field.
If you watch that whole video, he shows how the electromagnetic energy moves from the source to the bulb, and the length of the wires is irrelevant, and it moves just as quickly.
Yeah, but it's not that it's irrelevant. It is relevant locally in that you had any electromagnetic.
Yeah.
At different, small, along the cable.
Yeah.
The electromagnetic field that were there. Right?
Yeah.
And the motion of electrons local, that is slow, and the electromagnetic field, the magnetic field around the cable, allow the energy field over a long distance, because there are many that were like in series. You see what I mean?
It may serve.
They were like this in series.
Yeah.
It was like a string.
Yeah. It may serve you to watch that video, because he actually talks about the length of that string and what that means and how it's irrelevant to the transition of the electromagnetic energy. So really cool. Any other comments or questions? Because we do have a few minutes. If we start closing now, we will be gone. And I think this torque thing directly relates to the electromagnetic energy. And because it does relate to Bucky's 6 degrees of freedom, please indulge.
But Steve, What, just indulge with me 1 second again.
Okay, go ahead.
The length was irrelevant because there was a local efficient
Yeah,
transmission of something. That's why it's like a string. It's like a vibration. You understand what I'm trying to say? Locally, the electron was moving like this, just small.
yeah,
There was a magnetic field around it. You saw that? The small rings,
right.
right?
The rings are
That
spheres.
local created the energy field.
Yeah,
That touch, that was transmitted like this, fast at the speed of light.
yeah.
You get what I'm trying to say?
I think so. Yeah,
The length, that is the implication of time of travel become irrelevant.
yeah. Well, the electrons
Because
basically,
it's locally instantaneous.
yeah, the electrons actually virtually do not move in the
Yes.
wire. The electrons aren't moving at all. The energy, though, is moving in this spherical fashion outside of the local identified event, invisible.
What that means is that locally, the electron fields, the field created by electron were like a chain. Since it is a field, that chain, that what constituted the instantaneous enabler of the energy field.
Yeah,
From the battery to the light bulb.
right on. Okay, let me indulge me, guys, and if you can cuss at me if this isn't worth it when we get done. Here we go. Okay. What just happened?
And I've been following this series by Destin on Smarter every day about helicopters. And gyroscopic precession is just one of those things that still blows my mind, as it did Destin's. So I'm here at the University of Sydney, my old stomping grounds. I'm going to borrow some of their lecture dem equipment to hopefully teach you a bit about how gyroscopic precession works. First thing I need to do is talk about vectors, because a lot of things in physics are vectors. That means they have direction. So an example would be momentum and force. Those are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction. And if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it R. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now, before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way. And so a torque pushing that way actually swings this angular momentum around that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around, except not for long because this appears to be a quite frictionful wheel. So check out Destin's other videos about helicopter physics, and then come check out my channel, Veritasium, where you can find more like this. Except I don't often nearly get my head cut off by a bicycle wheel. So.
Okay. So I just was really
What's it like to learn science on Brilliant?
sorry.
Brilliant.
I was just really excited by this concept of torque, spin, trajectory, and spherical energy. And I think it all pertains in some way. Anyway, comments, questions?
That is the way Bucky demonstrates the precision, basically. You remember the hammer thrower or the disc thrower?
Is there a video of him doing that?
No, there are pictures, but that's what he talked in this time. You know, when you look at in his writing, that's the illustration that he takes to demonstrate precision. When you have a hammer thrower, it builds angular momentum to a certain level and then releases a disc that goes in the direction that was perpendicular to the direction of a momentum. Remember that, Susan?
I'm not sure if it's still in the Olympics any longer, but
No, it's still, you know, like the hammer throwing is still in the Olympics.
in track and field, yeah.
And yes, and the disc throwing is still.
It's we're past the hour and a half. Part of me wants to go into the jitterbug video, but I think that would be better next week when we finish spheres, because I want to go next week from the sphere to the tetrahedron, which is driving me crazy. I'm not sure how it does that. What?
Pumping action in the vector equilibrium.
Yeah. Okay. So, but I don't know what we're doing there. So maybe it's just time to, any other comments or questions, any other suggestions, or shall we end the call? Okay, let's, what? By the way, precession is the word used for torque. Torque-induced precession, gyroscopic precession. I used the stars as I said precession, and John corrected me last week saying procession. But I noticed that torque has precession, and precession is one of those elements of the degrees of freedom that Bucky likes to talk about.
But what is there? You know, Wikipedia is not correct.
What's what? What's not correct?
Not correct. It's not correct. It's not a correct definition of precession. Precession is an independent.
Is an Bucky, it's an independent aspect, just like spin and just like torque. Yeah,
yes,
I got that. But it was interesting. The word precession is used in describing torque.
Yeah,
gyroscopic torque. Any other comments or questions? We discussed on Wednesday briefly about how the Greek concept of spheres may have influenced their entire philosophy of way of life, just like Bucky's concept of spheres can affect the way you and I understand the way the universe works. The thought came up was that maybe the Greeks, their limited idea of what occurred in a sphere may affect their philosophies. And I had a conversation with Joe. Joe, I don't want to put you on the spot, but is there, maybe I shouldn't even be asking, but we've talked about it on the side, but I've never gotten clear myself. Did the Greeks' limited concept of spheres and planar geometry affect the way they related to the universe in ways that aren't just obvious to us right now as we're looking at Bucky? Is there some specific philosophy or? Go ahead.
Yes, I mean, and they looked at it as basically that everything that they can set, everything that they perceive could be quantified. And then how did that factor in to their perceptions and what their quantifications and what that meant for things like future philosophies of like utilitarianism.
Right.
So it factored into their ethics as well.
So
and
you're
how they
saying, go
Go
ahead,
ahead.
how they went. I don't want to interrupt you.
no, go ahead.
So you're saying that they were all into like this planar, this sensory. If you can't see it, it ain't real. Is that what you're?
That's
know?
correct. Yes.
Is there a particular, like you talked about empiricism, you talked about
Epicureanism.
Epicurean.
Yeah.
Talk about those for a minute, because these Greek philosophies from Plato and Socrates, these guys affected Western civilization. Descartes started breaking that chain, but he was still stuck with this sensorial idea, the Greek concept. Go ahead.
Yeah, I mean, I don't have my notes on it, but I mean, essentially, yes, this idea of their senses and how they essentially looked at the world is they looked at everything that needed to be, how they applied their logic and mathematics to it. And then that's how they just made their decisions. So based, I mean, I don't have my notes on it actually.
Yeah.
So I wish
Well, I put you on the spot, and I apologize because we didn't get clear, but I think that's interesting, that this idea of this sensorial experience, that's why they were excited about stars being in a dome, and that was okay with them.
That's right.
know?
That's true.
Whereas as we started to look at it, like Galileo, suddenly he saw, I've got a moon going around Jupiter,
Right.
So it can't, everything's not in a freaking dome, and I can prove it, right? And we took that Greek idea and went from Ptolemy, which was a geocentric idea of the universe, everything spinning around the earth. We went to Copernicus, where he said, no, it's solar centric, right? But we still were stuck with because we didn't see beyond that. And I guess it all comes down to calibration. It all comes down to the smaller my unit of measure, the deeper I look, the more I see. And now I see that there are things I don't see that are just as real as things I do see.
Right. And that's what they didn't get.
That's what they didn't get. Yeah.
But we have to say that everything, and that has been the process that we follow, the scientific process, is nothing is established until calibrated.
Yeah.
It's still a theory until calibrated.
Yeah.
When it's calibrated and measured in a way that is repeated most of the time, and then is verified with experience, with observation, then we bag it as scientific knowledge, because it can be repeated over and over.
And as I studied Mandelbrot set, what I learned was the smaller I calibrate, the longer the measure ends up being. And the explanation was, if I take, and they used the island, the UK, the island of the British Isles, and they said, if I use a mile-long measure, I'm going to miss some of the indentations. And if the shorter my measurement is, the more of the indentation I'm going to catch until I get really small. And then the shorter my measure, the smaller my calibration, the more I will see. And I like to call this inspansion.
Yes. That's why I always understand finite in terms of calibration.
Yeah.
Finite means you can count,
right?
You can measure.
And
because if infinite, you cannot measure.
Yeah, and we're at the bottom of this paragraph on spheres. Bucky starts talking about units so small that they're not measurable, and maybe we have just the 5 minutes to do that. We can talk about that visibility factor that he talks about. Let's see here. Yeah, we showed that. Oh, maybe I didn't include it for some reason. Let's go back up to the top here. I'm going to share the screen again, and then we'll just finish this bottom paragraph. And we talk about when it gets so small, we can't see it. So John, are you still with us? And you want to start with as the frequency and then finish the whole sentence off?
As the frequency of triangular subdivisions of a spherical constellation of omnitriangulated points approaches subvisibility, the difference between the sums of the angles around all the vertex points and the numbers of vertexes multiplied by 360 degrees remains constantly 720 degrees, which is the sum of the angles of 2 times unity of 360 degrees, which equals 1 tetrahedron.
Somehow, when this omni-triangulated points approach subvisibility, all of a sudden there's a tetrahedron. I don't get that. And I think we'll leave that to next week. Okay. Any comments or questions? I mean,
Every system is divisible in tetrahedron.
yeah.
You get me? The tetrahedron is the unit of account.
Right. We'll talk about that next week. We're going to save that. When we start next week, we're going to start right there.
So below the tetrahedron, you don't see. You don't see. You cannot count. It's subvisible. You cannot count what you cannot see.
Right on. Okay. Whoa, we made it through that. Thank you, guys. Hey, so Joe, how are you feeling and what's your takeaway today?
I'm feeling, I see where we've gone in the past when we were talking about topologies and topographically and how these, what was meaningful. The pointing vector analysis is actually something that I'm still continually thinking about. And what Susan's explanation about how energy flows to the point of least resistance, which we have talked about in the past, makes a lot of sense to me. And then starting to seeing that vector, that momentum and force video actually clicked for me for something else. There's a company that I know that used momentum and force and actually sentiment, like literally sentiment analysis and the velocity of a conversation. And they would actually have, the company is $1 billion company now, but it's very early on, I got to know them, and they were basically able to predict what was going to happen next by using, and I'm seeing that there's got to be a connection between what they were using as far as momentum and force, and like it was momentum and velocity and force, and the way they were using their mathematics and what we discussed here today, and I'm just not sure of it yet. But at some point, I can actually share something with that at some point. My mind's going to, but I know that this group can make those connections for me. If I can find something a little bit more updated about what they're actually, how their algorithms work. Anyway, so my mind's going in 100 different directions, to tell you the truth, which is actually kind of cool. So that's what my mind is spinning. So that's what I'm taking away from today. Susan, how are you feeling? And what are you taking away from today?
I'm feeling pretty calm. I feel like we've been going over this and limiting to just a couple sentences kind of lets me feel like we're getting through it. I know I still have so much more to understand. But what I really did get today was just, again, the importance of perspective, like how far up, how far out, because up is maybe not a term I want to use. So what can I see from there? And if it's not about me seeing, can I apprehend into the next thing that I'm going to want to understand? And so lots more connections to make. John, how are you feeling and what are you taking away?
Wow, I'm not sure I can even answer that question. Been an interesting journey, wandering, digressing. I mean, lots of thoughts, prompts, some tapping back into previous thoughts. Still am not sure where my sphere is or going, but it was just interesting to be part of the exploring. So I just want to let the mind do a bit more wandering about some of the things we've commented on, been exposed to, everything from energy, and the way energy works. As I say, it's not a current flowing that's used up. So much is different in reality, especially when you look at the smaller particles and measurements than, I suppose, what I was brought up to believe or understand. So yeah, that's scattered thoughts, random thinking. So it's been an interesting morning. Nelson, so how do you feel and what do you take out of today?
Thank you, John. I'm feeling very well. My apologies, I was late. Thank you for this call. And I take away. I don't understand very well all, okay, but I take away more about the perceptions and the flow energy. Is important to continue in move. That I feel, and that my takeaway. Thank you. Manu, what do you feel and what do you take away today?
I feel good. Thank you, Steve, for really kind of leading this into the direction that way. You were able to always bring back to something. But what I take away from, I don't want to think of spheres as anything else, but arrays, constellations, and interacting to form local, what you call locus, is the intersection of things that increase the density or the contrast of things happening in a way that becomes local into something that there is a boundary. And it's something that is always related. This geometry is a geometry of relations and interrelations. And it's always evolving. It's not anything static. And this flows from first principles, that there is energy, energy flows, energy always flows, energy flows to the point of least resistance. The point of least resistance is the valleys of that locus, because locus has peaks and valleys. So energy flows to those valleys until it is plane again, and then it flips. That is unstable equilibrium, flips again and flows. So that's all that I know. And secondly, because of that finiteness, because of that curve, then there is periodicity, right? There are cycles, and all flows again from there. So in my designing of my local, if I'm awareness of those, that would definitely influence the way I live to the direction. That's why I wrote here. With Becky, I carry the scars of my life. I'm not ignorant to them. I know that a sphere doesn't exist. I know that it's spheroids. It means that in there are contrasts of concentration and less concentration of whatever. It's not uniform. So therefore, carrying like that, I design in a way that we last week talked about the franchising model. I don't know if he was here on a Wednesday that we talk about that. In that locally, it is tight in terms of designing relationship is clear. Yet it keeps the flexibility of the relationship between those packets, between the array of the franchise system. In that, when you are local in the franchise, there are relationship and flow of energy that is pretty much determined. There's a hierarchy that has to follow. But in terms of relationship between the different franchises, it is very, very flexible. It flows in a different way. And that's how I see the way I design either my business or my life. It is designed in a way that, like Bucky, you build struts and things to whatever is happening to create a world that is, I wouldn't say stable, but that is stable in a way that is anti-anthropic for a certain while, to the extent possible. And that's what I take from this discussion. It's not so much like the understanding of the mathematics of geometry. It is more of how can I use that to apply to my environment. So again, I'm very, very thankful for you to take the time for us to be together. Who is it? Kelly, how do you feel? What do you take?
Kelly left us.
He left us, eh?
Yeah.
So you, Steve?
Yeah.
How do you feel? What do you take away?
Well, I feel really honored and almost embarrassed because I don't know how to do this any other way than what I'm doing it. I don't know how to do this other than to just ask the questions. I marvel that I've really been committed to pursuing this on the idea that I don't need to know the math. I don't need to know the formulas, that I can understand the concepts and the benefits and the benefits and the consequences and the implied realities of the concepts. And I don't need to know the math. Einstein changed the world and he didn't know the math. He just had a dream about a train going by him and figured out and heard the sound change. And he figured out the nature of the universe and changed everything. So I'm kind of like willing to do that. I really enjoyed when Joe talked about momentum and velocity and spin and this idea of this company that he found. And, you know, I was thinking when I saw the torque thing going and I saw spin, I'm going, wait a minute, we're doing that politically. It's political spin. And when I put a spin on a topic, then I create torque. You know, there's this energy going in a certain direction. And then I put that together with what Joe said. And with our current way to do deep field analysis, the way we can take this AI and we can take all of the communications and monitor the words going on, we can actually measure the momentum, the velocity, and the spin on all the words that are happening in the media. And we could actually predict a torque off of that. But if we did, we'd be forgetting we'd be looking at the local and forget about the non-local, because I don't know how much longer these people that are so quiet are going to put up with this crap. You know, at some point, people are going to say, I'm not doing that, right? And you political guys can hang out over there. There's this non-local energy that's invisible that can, hopefully, I'm hoping, compensate for all this momentum and all this energy we see in all this political spin crap. Somehow, Bucky's theory, spheroids, Bucky's precession applies in every aspect of my life. And the very fact that human beings would call spin, the use of word spin, shows there's some inherent comprehension of those principles. We know it. That's why we call it spin. I don't know. I'm just honored to be here. Thank you for your patience. We probably should turn this over, let somebody else be the guide. And thank you guys. I'm just really grateful. We'll see you the next time around. Peace, everybody. Peace.
Thank you, Steve.
You bet. Thank you, Manu, very much. All righty, bye-bye.
Ciao.